with Sawzall?
To cut through the cars. Ideally, they're using like the Jaws of Life thing that you've seen. It's actually hydraulics, and it's hydraulics with just very pointed pieces of metal. But it's the power of the hydraulics that actually cuts it, because the metal itself is too hard. You just need that big sheer hydraulic strength to be able to break it. And so it's actually a pretty slow process. Okay, so I apologize for that delay. You guys got me off on a tangent, right? Which is kind of easy to do. Surprised you guys haven't figured that out yet, that you can get me off on a tangent, right? So let's talk about stairs. And I couldn't just sit and talk about just normal stairs. So we had to have a little fun with stairs, and we had to talk about kind of the kooky stairs. I'm going to talk about terminology first. Then we'll show you a bunch of kooky examples that I think are just kind of cool. And then I'm going to show you how you would do the kooky examples from a construction standpoint. And so we'll work through there. So I'm glossing over some of the basics of how you construct a stair into kind of the more tricky ways of constructing a stair, which is a little more fun, I think. So, but in order to understand stairs, we do have to start with the basic terminology. And at its most basic level, it's broken down into two things. You have a tread, right, which is the top surface of a step. It's what you can actually put your foot on, right? And then you have what's called the riser, which is the vertical section that's in between each stair, right? It doesn't have to be. You could have an open staircase that doesn't have a riser, but you have a tread and a riser typically on any set of stairs. So if we're looking at a set of stairs in section, right, our treads are right here. It's that horizontal piece that you can step on, and our risers are these little vertical pieces that come up here. Okay? We have a little bit of other terminology that we'll talk about. A stringer, right, is the support that spans this opening, right? And so you can see down here we've got a little bit of a thrust block. It's a little piece of block that doesn't allow, if I were to standing here, right, this would naturally want to push out at this end. So we have something that's holding this from pushing out, right? Likewise, we have a block here that this is resting on. It could be a joist hanger. That's the other way of doing it. And this is that header in the floor opening that we've talked about before. We have several different configurations of standard stairs. We can have our straight linear set of stairs. This is in plan view, right? We can have an L where we have a little bit of a landing. We can have a U where we have a bigger landing and we wrap back on ourselves. We can have a partial spiral where we have a straight set, an angular set, etc. This is like an L, but we've eliminated the landing. And there are certainly code requirements about the minimum depths here of what the treads would be, right? This is far more common for what we're going to see in practice today because of the minimum requirements that you have for actually wrapping. Usually in residential, this dimension, this small side of the stair, if it's wrapping, has to be 4 inches. Right? That's kind of the minimum piece. A lot of the examples that I'll show you don't have it that way because they're more architectural stairs than practical stairs. So if we look at something like this, we can see it a little bit better. These are our stringers, like I said. They're cut in that sawtooth pattern to support each of those stair treads and stair risers. This is a wall stringer, which is kind of a trim piece that would go on the outside to cover up that jogging system that's here. That would be optional, not necessarily installed. Certainly if you put carpet over the stairs, it's sometimes not there, sometimes there. Right? We have railings and that sort of thing, which are additional to these. So we move into something, this is like the nomenclature tell-all that could spend a little bit of time actually going through. So we have a couple different things here. We have a length of a flight, which is the overall flight of the stairs, which is from the bottom to the top of the stairs. And we have what's called a length of run, right? And so that's between a landing, right? So a length of run would be between this landing and the top of the stairs. We would have a length of run from the bottom of the stairs to the landing itself. Does that make sense? Right, so we're breaking that. And there are code requirements for how many stairs you can have in a row and how long that length of run can actually be. Right? And they vary a great deal. If you're in Europe, for example, you can have an almost infinite, depending on where you are, run of stairs. Right? And those were built a long time ago. We didn't need landings. Here in the US, we're going to have landings that occur every 12 stairs or so. If it's residential, you can get away with more, right? And so it's going to vary depending on if you're in commercial and that sort of thing. And that's so that we can have a rest and work off our cheeseburgers and that sort of thing, right? And it also means that if I were at the top of the stairs and I tripped and I fell, I wouldn't fall the full length of the stairs. I'd only fall to the first landing, right? And so those kinds of breaks do help, right?
If you've never done moving, that's
what?
If you've never done moving, that's really integral to landing.
Right.
Trying to get something around, like, it's almost impossible.
Yes.
Even if it's elevated.
Yeah. Exactly. So the riser, right, which we talked about, does have minimums and maximums of height. Those minimums and maximums are not things that I'm going to make you memorize, but they are different if you're in commercial stairs or if you're in residential stairs, right? Residential stairs can be steeper, less people using them, therefore they can be steeper. Commercial stairs, more people using them, they're a slower rhythm to the stairs, right? There are certainly minimums as well for the tread depth, right? So how deep can a tread be? And that's going to vary whether it's commercial or residential. So you can have narrower steps and steeper steps if it's in residential, longer steps if it's in commercial. And I think one of the important things to think a lot about stairs is that stairs inherently, and this is more of a design perspective to stairs, stairs have a rhythm to them. And so when you're thinking about a set of stairs as a designer, you have to think about what is the rhythm of the person who's walking up the stairs. If it's a very steep set of stairs, it tends to be a much more labored, like you're lugging up the set of stairs, right? If it's a long, shallow set of stairs, it's a more leisurely pace as you're walking up the stairs. The worst thing that can happen is stairs that have the wrong depth to them, right? Where you have 1.5. So you're walking up and you don't really know, should I skip? Should I, is it like, and it's an awkward process when you're walking up and down the stairs. And so when you're thinking about designing these stairs, think about the rhythm of stairs, right? There's also a certain practice in stairs where you want to think about how many stairs you're going up. And it's awkward, especially if you're in the 1, 2, or 3 stair range, to end on an even number. And so if you think about hiking upstairs, right, you got to put yourself into the mindset of working up stairs. It's easier to lead with my right, and I work up the stairs, and I end on my right. Right? There's a natural rhythm to that. Or if you lead with your left because you're left-footed, it would be the same thing. There's a certain rhythm to that. Where if you're off and you think about going up a stair, right, and then all of a sudden you're off rhythm, it can get confusing. And so when you're thinking about designing stairs, you want to think about how many stairs are involved, and it wouldn't hurt you as a designer to actually go out and try to pretend to walk up the stairs to think about, can I do this, right? And so there are certain minimums that you can obviously use as a guideline. There are all kinds of books, the graphic standards, for example, that will talk about what stairs should be and rhythms of stairs and that sort of thing. We can have circular stairs, right? Spiral stairs, that kind of thing. We have certain minimum tread depths that we have to achieve depending on where you are and what the building codes are, which limit how tight the arc of stairs can be. Right? The truth is about spiral stairs is everybody thinks they'll take up more or less room. They actually take up a lot more room. They're very awkward, but they can be done, and they're certainly very decorative. If we think about the slopes in stairs, right? We have ramps. 1 and 14 is a wheelchair access. You can go to 1 and 12. 1 and 8 is a ramp that you could walk up, but it's not wheelchair accessible. If you had a steep driveway or something, it might be 1 and 6. Might be more than that. We can have basic commercial building. It's going to be somewhere in this 18 to 38 degrees. This is for non-habitable rooms if we start to get too steep. So if it's just storage, it's an attic, something like that, you can get away with a steeper flight of stairs, right? This is going to be ship's ladders, those kinds of things. We can move all the way up to portable ladders, like I'm going to climb up on our roof, right? And those are much more vertical. And so it's gonna vary a little bit depending on what you're doing. Another example here of our stringer. It's cut out of a 2x12, right? We cut this jog pattern out of it to be able to put our treads and our risers on it. So if we think about very, very simple stairs, right? All we're trying to do is provide a flat surface to be able to walk on, and we're trying to step that surface up. And so this is something that's relatively simple. It's framed in wood. It has a gravel that's been applied to it that gives it a nice walking surface, and you can walk from one level to another outside. Right? If we've cut our stringers, right, and we're actually installing this is on a deck, a little worried about this as the foundation for their deck. I think they're going to have long-term problems, but whatever. So in this particular example, we have our stringer that's been cut. This is using a joist hanger, right? And remember that the bottom of the joist hanger really doesn't matter. It's the attachment points on either side. And even though you think it rests on it, it usually doesn't by the time it shrinks. Sometimes, depending on this placement, you may have to notch the bottom of the stringer to allow that joist hanger to fit. And so that can happen. And obviously, they've laid out their lines for where this is going to go. This is not one of my projects, but you guys get the idea. So we've got our lines laid out. We're going to lay our treads on it to get up to this deck surface. So if we were actually laying out one of these stringers, sorry this is a little bit blurred, we can use a framing square, right, to measure our height and our width and be able to mark that and then cut it out. Ideally, we'll try to cut out all of our stringers at the same time so that they match. You could cut out one as a template and then cut the rest of the stringers from that, though there are some accuracy issues that can arise the more times you copy a particular piece. So let's move into some fun examples because we can, right? So architects love to design these sexy, swoopy stairs, but they still have all the same principles that we've talked about. They still have risers, they still have treads, they still have to have consistent height. That's one thing I didn't put in the slides, but we should talk about. Your body is incredibly good at memorizing a dimension. And so if you walk up, how many people have walked up the stairs and tripped halfway up? Right? Okay? That little trip point is because one of those stairs is slightly different than the rest of the stairs. Right? And so the gateway for that is going to vary depending on personal sensitivities to it, but it's usually somewhere between 1/8 of an inch and 1/4 of an inch, right? I'm pretty sensitive to that. I've noticed that where if it's more than 1/8, I'll probably trip for whatever reason. That's how my feet work. But when you're walking up a set of stairs, if it varies more than that, your body is programmed. So as soon as you travel more than 3 stairs, your body has adapted and knows what the height of the next stair is going to be. Right? And it expects that height to be there. That's part of walking up a set of stairs. And so if one of those is off by 1/4 of an inch, chances are you're going to trip on it. Right? And so stairs need to have this consistency. And so no matter if you're an architect designing a really whacked out weird set of stairs, that consistency still has to be there because you have to be able to walk up and down that set of stairs. Right? And so some of these things will not meet code, and I'll forewarn you that they don't necessarily meet code. But sometimes they're nice examples. And so in this particular case, the railing itself wouldn't meet code. It doesn't have small enough openings. A baby could fall through it. So it wouldn't meet code here, but there's a certain architectural quality to it. So if you were adapting it for use in one of your buildings, you could certainly change the railing. So in this particular instance, we have a steel stringer running up either side. Right? It's not one of the stringers that's been cut out. In this case, we're fastening to the stringer, and because it twists, it's an easier method of doing it. We have our treads that work their way up this particular stair. Same thing here. This one's much steeper. Probably wouldn't be code either, right? But what else is new? In this particular example, we're using a folding set of steel that's been attached to the wall, and this folding set provides each stair. Right? And so it has this pattern to it. Obviously, there's no railings whatsoever, right? But again, this is architectural, not necessarily practical. On the right here, this is a concrete stair. Again, there's probably a few issues with railings, but whatever, right? Again, what railing?
There's glass.
But yeah. So if you really want to make this stuff code, there are ways of doing it, right? So in this particular instance, it's a concrete stair. All right, it's built on this helix, and we're using only one stringer, and it's this internal piece that's acting both as the railing and as the structure for this stair itself. Right, and so this is one beam that spans all the way up to the top. Right, and the set of stairs wraps around the outside of that particular stringer. Right, and so the stairs are cantilevered off that. Something like this might actually meet code, which is nice for once. Right. Maybe not down here so much. But in this instance, we're using solid blocks that are representing the stairs. This is being supported by this wall that's underneath, which is pulled out, which is why there's a little bit of a gap that's against this wall, right? Which highlights the texture of that wall, and it gives us an opportunity to light that wall from the side, right? So we're tucking a little bit of light down there. The gap is not big enough so that we're worried about it for safety reasons. This side here could be supported by all of these cables. My guess is they're a little bit more decorative than that because we've got so much support from the wall underneath, and the wall isn't halfway. It's actually pulled out a little bit this way. So if we were using those cables, they would actually have to be in compression, not in tension. But anyway. Another example here, this is kind of mid-construction process because we can see the welds haven't been touched up yet. These little stripes come down, each one of them is welded and then comes across to form the tread of the stair and then goes down again. Right? The nice thing about an open set of stairs like that is even if the stair treads themselves are narrow, it does give you some toe room because your foot typically is your shoe is certainly longer than where you walk, and it gives you a little bit of space for that. But this pattern gives us a nice pattern. It's kind of a floating set of stairs built out of steel and taking advantage of that. This is a floating set of concrete stairs, right? This is the kind of stair that could be pre-manufactured, right, in an off-site fabrication setting. So it could be made ahead of time and then brought to the site, delivered to the site as a pre-manufactured piece and lifted into place. Could be site cast, though there would be a lot of work framing in for this because there's another stair below it. And given that the backside isn't a smooth surface, I think it's an awful lot of work that I don't think would be done in a site cast example. So you're careful about that. You know, they're playing with the light settings to be able to let the light come on either side. And again, there's not really any railing. So, couple other examples here of the spiral stairs. This is done by the same company that the last set of stairs would be. This is a set of stairs where the stringer is right in the middle, right, of the set of stairs. It's cut in a sawtooth pattern on the top side to allow those stairs to rest. This would not meet the minimum dimension for a set of stairs. So. Once again, we do have some issues. So this is an example of a set of stairs that is floating. The structural support is this wall, right? The steel stairs are most likely welded to steel plates, and I actually have a construction example of how this would be made that I can show you a little bit later on. But on something like this, the architects are playing a lot with the pattern that these stairs make on the wall and the way that the wall and the stairs work together to create this shadow pattern. Right? And so, for example, if you were in Rhino and you wanted to do something like this, right, you could make all these little patterns appear, right? Maybe. Anyway, it's another example here just showing you it has a nice little pool underneath to enhance the reflections and what have you. Another example here where we have a block that would be the buttress. This is a big beam that's spanning up to the second level, right? All of these stairs stick out from it, which means they were most likely manufactured after the stair and then inserted into place. They could be steel stairs that are covered in a material to look like they're concrete. Very unlikely that they were manufactured or cast on site. Another example here. This has, it's kind of a cheater set. We have glass railings and glass treads. They're frosted glass treads. In 2 weeks when we talk about glass, we will talk about structural glass in the way it's being used today, but it does have a little bit of steel that runs up the bottom there, which is providing a lot of the structural support. We can see it up above here, right, providing that support for all that stair. So it's a steel stringer. Different set of stairs here. These stairs are actually supported in tension from all of the network of cables. The cables are doubling as the railing for this system. So all of these little, and it's obviously two helixes that are woven. So you have one set of stairs on this side, one set of stairs on that side, and this mesh of cables is providing the railings on either side to make it more stable. Example of glass stairs that are supported by steel. There is a steel stringer on this side. There is a steel stringer on that side. The fronts of these are steel. The tops are glass, but there's a light underneath to provide that. Likewise, the railing itself is made out of glass, which is kind of a very common sort of thing. Here we have a cantilevered concrete staircase. So we have the nice concrete wall. You recognize the form ties, so you know it was cast in place concrete. Right? All of these little stair treads, right, were probably cast in place. We don't know for sure in this particular example. They could be welded steel, and then the steel is then encased in concrete. It could vary a little bit. My guess is that these particular ones were cast in place. Right? This one's pretty fun because they're playing with the fact that there should be a pole in the middle. Right? And obviously it's not there, and they're playing with that. The bulk of the stair is carried by that steel stringer on the outside. And remember, since we can weld steel together into a monolithic piece, we can do these kinds of cantilevered things with it. Another example of a set of wood ribbons that are providing the basis for each stair. There is steel under each one of these that are providing the actual support for this kind of a system. This example, we have laminated glass stairs that are strung on a stainless steel stringer, providing that spiral. Those obviously don't meet code. Another example here, these are hung. These are the opposite. They're hung down with these walls on either side. There's two of them. I don't think this would be a particularly pleasant staircase to go up. I think it would be very dark and unpleasant, but nonetheless they exist. Right? Another example here where this is kind of basic, right? We have the steel pole in the middle that's providing the primary structural support. We're floating around the outside, but we've used this glass block wall, or this glass wall, to provide the railing on the outside of the stairs. So it becomes a very transparent staircase. A little bit of detail just with the frosted glass in juxtaposition to the wood blocks. Another example there, same stair. All right? Wrapping up through this kind of library to an upper floor. This wall piece / steel is actually acting as the primary support for this particular stair. Okay, this stair is hung from the ceiling. We see our tension cables coming down from the ceiling. That's providing the structural support. So we end up with a much thinner set of stairs. There is no big stringer underneath. It's a much lighter weight set of stairs. I would be a little bit worried about what this would do in an earthquake type setting. Notice that it has no base really on the floor, a couple little pins, but this is the kind of thing that's going to move in an earthquake, which makes me a little nervous. Another example here, where the stringer is cast in place. Each of these is added after the fact. Right? Chances are it's welded or bolted into place. Steel cables coming down, right, supporting the railings, supporting the stairs themselves. There's a steel stringer on the inside, though, that's providing a lot of the structure support. I couldn't resist, right, because it's kind of fun. I don't know, this very easily could have been computer generated, but you get the idea. It's entertaining. It would freak you out if this were the staircase you had to traverse. Another example here, we're attaching to the wall. We're also attaching to this glass railing here. The glass probably is providing some structural value to this. Based on the thickness, my guess is it's laminated glass, so it's meant to be used structurally. You also have a lot of weight that you're dealing with that glass wall. So if these were just steel stairs that were welded into a concrete plate here, I would be worried about how much weight is being added. So at least this is self-supporting, would be my guess. All right. Another example, this is concrete that's been skinned. Of course, they're playing around with the colors a little bit, which is entertaining. Another example there. Okay, so the big question is, I showed you all these really fun examples, and this is a construction class, not a design class. So in order to legitimize my showing you all those fun examples, we do have to talk about how you would actually make something like this. And so I have a variety of pictures that might help us to understand how something like this is made. So in this particular example, we have a concrete building site where we're casting in place a wall, right? You should recognize that we have, in this particular example here, right, we have our form ties with our plywood form boards, right? We have our studs that are running up and down vertically. We have our wailers, which are running horizontally, right? And we have those nice little metal clips that are holding those form boards the correct distance apart, right? That's the back side. If we move over to this side, we still have that formwork there, but we have additional formwork that's being done on site down this side. And I think the next slide has a little bit better. This is with the formwork taken away. We only have one side of the formwork right now. Here's one side of the formwork. Right, we're putting all our steel in. Notice that our steel is coming up, tied well into the wall. That steel is then running out into where those stairs are going to be cantilevered. Right? And so there's very specific placement for how this steel is working, and it's becoming an integral structural unit. So it's not something that's added after the fact. It's part of casting this wall in place in the first place. Right? So we're using all this stuff together, right, to be able to build this. So we're back to the side of the wall. We're starting to build this upper set of formwork here. If we look closely, this is the underside of our stairs. Look at the amount of rebar that's in here. Right? So this is a major structure going on. This ramp is just for access, so you can actually finish off the set of stairs, etc. There's a lot of shoring that's happening underneath that set to be able to support the weight of the concrete before it's had a chance to cure. Right? Then we're going ahead and we're pouring the concrete, right, into place, and we're finishing the top surface of that concrete as we go along. Notice the plastic that's covering it, keeping it from getting wet. It looks like maybe it's raining, so they're making sure that that's keeping it the surface moist, so we're not getting those surface cracks, right? And now we move on to stripping off the formwork, right? And so we're going to start to strip off that formwork. We strip off the formwork underneath. We get that wall, right? We're looking at the undersides of the stairs. Chances are this is after the concrete's had a full chance to cure, because you would reshore that because it's way too much weight until you have that chance. And so they're continuing on with the construction of the building. Here's some reshores that have gone into place. These are just temporary to hold it into place so that there's not too much weight on this. And you can see very easily that we have our wall, we have our cantilevered set of stairs that's running up that wall. My guess is that something else is going to happen with the set of stairs. It's going to turn and come down here. It's going to turn and continue, or something like that. This was the part of the wall that they were working on creating cast in place. Right? Does that kind of make sense for how they make it? Okay? So here it is once we get a little bit further on. There are a few ties that have been left embedded, so my guess is that's to tie in a railing system or something down the road. Obviously this has had enough chance to cure. We're further on down the site. We're seeing more of the building site up above, etc. Right? It's a pretty nice staircase to put going down into a basement. So my guess is this is a multi-story gallery space or something that's sunk in. And I don't know off the top of my head what it is. Okay, so we have a different example here. This is where we're going to be creating individual cantilevered steps as opposed to the single monolithic unit. In this particular case, there is going to be a cold joint, right, in between the wall material and the stair material. And they're actually casting every other stair. So they're going to do this in 2 different batches so that they have the flexibility to work around it. So if we're looking at this particular photograph here, they've cast this stair and they've cast the second stair, or the third stair there. They've skipped this stair and they left it uncovered for now. They'll come back and do the opposite set of stairs. Yeah?
So the 2/3, 1/3 like principle doesn't apply for these stairs.
Right. So the 2/3, 1/3 principle applies for light wood frame construction, right? Where we're trying to do those cantilevers. If you don't want to do any special structural support, the 2/3, 1/3 rule is a good rule of thumb, right? So even if we had a concrete slab with column, 2-way slab or something like that, or if we had a steel building that had this kind of a cantilever, we'd still like the 2/3, 1/3 because we don't have to do anything special, right? In this particular instance, we have to have huge rebar that's going to tie, right, that weight, that tensile weight that's on the edge of the stair back into the wall, right? So we're doing special reinforcing to accommodate that. It's kind of like if you did a cantilever on a light wood frame that was less than that and you flip the joist hangers upside down to be able to support that. It's a special circumstance where you have to do something. So the 2/3, 1/3 is just a rule of thumb for not having to do anything special.
What is that?
The 2/3, 1/3 rule in light wood frame construction is that if you have a cantilever, right, we have a piece of the building that's extending beyond its line of support, you have to have 2/3 of the distance of the cantilever inside the building and only 1/3 of it extending out of the building. Right? So whatever your structural support is, let's say it was 9 feet long, you could have 3 feet of cantilever and 6 feet would have to be inside the building. Right? I picked 9 feet not because it was any number in particular, just because it was easy to divide in 3. Right? So, back to these stairs, right? Pretty substantial rebar that's going to be supporting these. We've got shoring that's underneath to support this edge when they're doing their casting. These are relatively thin stairs to begin with, but this is the look that we get after they're all done, right? So instead of having that continuous piece, we have individual stairs, one on top of each other, right? Notice that we wouldn't have had room to do each of these in one pour, right? So that's why they had to split it. The fact that this is a cold joint does make me a little nervous but the steel runs through, and my guess is that since it's an interior staircase, the chances of water actually penetrating that joint and causing rust and those kinds of issues is very minimal. Right? It's going to have some kind of a shell that encloses it, which makes me much less nervous about it. But it certainly has a very unique look to it, right, in terms of how they finished it out and that sort of thing. So another set of slides, so you can see the back side of the wall, right, and how it works together. It has a very clean back side and the floating front side. Okay, so sometimes you want this set of steel stairs, right, or a wood wrapped steel that are going to extend out beyond a concrete wall. And unlike the concrete that we just showed, where we had to have that rebar that came out and penetrated into the stair, in this particular example, all we need is a plate of steel that's right on that outer surface of the concrete wall itself, right? And so that plate of steel that's right on the outer surface is tied into the rebar that's inside the concrete wall. But since we can weld steel together into a monolithic whole, right, we don't need anything that's further out because we can weld one of these stairs to the steel plate that's in the wall. Right, and make it as if it were monolithic. And so in this particular instance, we're not worried about water conditions because it's an interior staircase, right? So we're not worried about rust and that sort of thing. So it's okay to have the steel plate, which is right here, right on that surface of the concrete. If it was an exterior condition and we had that steel plate, this would be a great place for water to get in and start to deteriorate the structure of the wall, right? So it's only allowed because it's on the inside. So they're going ahead and they're welding these stairs into place. The stairs have a bit of structure to them themselves. They're not just steel plates. If it were a thick steel plate, that this looks like, to me, somewhere in the neighborhood of 1.5 inches, 2 inches, this would be a really, really heavy piece of steel. And so we don't want that weight. So they've actually made this kind of like a mini I-beam, right? So there's a couple little eyes that are in here that are supporting the two diaphragms on either end, and that's providing the structural support for these. My guess is that if you walked up the outer section of this set of stairs, it would probably bounce a bit. It would probably have some flex to it, right? And so you can see it here going up. You can see it here going up as well. These could be left with some kind of an exposed steel surface. They could be covered in wood. They could be covered in concrete, depending on the look that was actually applied. And those coverings, right, are just the skin for the structural steel themselves. In this particular case, they're being covered with wood ultimately. So we get the look that the wood is actually protruding from the concrete, which couldn't really happen, right? We need the steel for the structural support because we can't really have that cantilever. Okay.
Even on interior for concrete with
Yeah.
metal, would you still have to worry about condensation or? any
It's
kind
not
of-
enough. I mean, you could be worried about it, in which case you could paint it or do something that would cover it up. But unless it was in a particularly humid environment, if it was around here, would not be something I'd be worried about. Okay? So, just a quick overview, just to remind any of you that walked in late that didn't hear me talk about the plan for the next couple weeks. Next week is optional. It's a review day. I will have a practice midterm to give all of you. If you have any topics you'd like me to review or cover again, all you have to do is tell me about it, shoot me an email, gadams@dvc.edu. I'll compile the list of anything anybody's confused about. We'll put those slides together. We'll give a summary lecture of those things. Obviously, I can't go back through the whole semester. Right? I can't give 5,000 slides justice. So I will pick the things that people seem the most interested in based on whoever emails me. It's designed to be a review session. It's for you. That's why it's optional. It's up to you. If you feel like you need it, I'd encourage you to come. Any questions you have, we'll go over at that point. The following week, so not next week, but the next week, the week after, so in 2 weeks, your project 3 is due, and we're going to spend the first half of class talking about glass. We'll cover glass as a material. We'll cover glass being used in structural ways and that sort of thing. And then the following week after that, so in 3 weeks, is the midterm. Right? You need the same Scantron form you've been using, the double-sided 200 question 884-E. You'll have the full 3 hours to do it. Bring your notebooks and your note material because you'll leave it up with me so I can kind of leaf through it and see how your notes were for the semester. It's not particularly formal, just if you printed out slides, bring those in, whatever it is that you did. And I'll take a look through that while you take the test. And after that, class is over. Right? So, that's it. If there's no questions, you're free to go. And we'll see you for a review next week.
I think the section that I might want, I don't know, you're probably